So far, we have motivated the reasons underlying the concept of vector space. We have provided three noticeable examples of vector spaces. Now it's the time to discuss the concept of vector subspace. Let's introduce this concept with an analogy. Imagine that you're interested in buying a house. Then you go there, you take a good look at the exterior, the facade, the windows, hopefully the garden, and so on. However, you will never buy the house without taking also a good look at the interior, meaning the bedroom, the kitchen, and so on. Why that? Well, because the interior of the house provides very valuable information about the house itself. It turns out that in mathematics is the same, meaning that each time we define a space, some of its subspaces are source of very important information, as we're going to see in detail in chapter 2. Roughly speaking, a subspace is a smaller part of a space which behaves well with respect to the structure that is defined on the whole space. Let's see what it means in the case of a vector space V. A subspace W of V should be a part, a subset of V, such that if we operate the sum and the multiplication by a scalar of elements of V, then we still have all the properties that we required in the definition of a vector space. Moreover, W must be stable with respect to these operations, meaning that when we restrict these operations to elements of W, we must still produce an element of W. The easiest example of a subset S of a vector space V, which is not a vector space itself, and so it is not a vector subspace of V, is given by V itself without the null vector. In fact, if you take a look at the definition of vector space, you see that the request 3 says that we must have the null vector in order to consider V a vector space. Since we have thrown it away, then what remains, the subset S, is not a vector space. This very simple example shows that we must take with very good care the definition of a vector space, and we cannot imagine that the linear structure that is defined on a vector space automatically is also well defined on one of its subsets. Let's give the formal definition of a vector subspace. Consider a vector space V over the field F and a subset W of V. Then W is said to be a vector subspace of V if the operations of sum and multiplication by a scalar of the field F restricted to the elements of W still verify all the axioms of linear structure that appear in the definition of a vector space. Luckily for us, we don't have to check all the time the properties from 1 to 8 of the definition of vector space. The reason is that all the elements of W, since W is a subset of V, are also elements of V. And so the associativity and distributivity of the linear operations sum and multiplication by a scalar are still valid for all the elements of W, because by definition they are valid for all the elements of V, and so also for the elements of W. Instead, what is essential to test all the time is if the following four properties are satisfied. Does the sum of any two vectors of W still belong to W? Does any vector of W have an opposite? Does any vector of W multiplied by any scalar of F still belong to W? Finally, does the null vector still belong to W? If so, then W is a vector subspace of V. Let me immediately give you an example considering the real plane R2. R is a subset of R2, and we can represent it geometrically by considering, for example, the horizontal axis. R is simultaneously a subset of R2 and also a vector space. So it is a vector subspace of R2. However, consider, for example, the segment given by all the non-negative real numbers, that is, from 0 to plus infinity. This is a subset of R2, which is not a vector subspace. The reason is that if we consider, for example, the element 2, which belongs to this segment, then we can ask ourselves, is this property here verified? That is, does it exist the opposite of the number 2? The answer is no, because the opposite of the number 2 should be here, but it is, of course, outside this segment. And so 0 plus infinity is not a vector subspace of R2. We are now going to see that we can further reduce these 4 requests to only one, and this will also give us the opportunity to introduce a concept that will remain with us until the end of the course. So let's discuss this theorem. Let V be a vector space over the field F, and let W be a subset of V. Then W is a vector subspace of V if and only if for any two scalars lambda1 and lambda2 belonging to the field F and any two vectors w1 and w2 belonging to W, we have that lambda1 times w1 plus lambda2 times w2 still belongs to W. We must prove that this only request contains as sub-requests those written here. This is actually very easy because if we set, for example, lambda1 and lambda2 to 1, then we remain with lambda1 plus lambda2 belonging to W, which is the first request. That is, the fact that when we have any two vectors of W, their sum must belong to W. As a very easy exercise, I leave you to check that if you perform these choices here, then you have requests 2 and 3. Instead, I'm going to discuss with you how this request here contains implicitly the fact that the null vector must belong to W. To see that, consider again lambda1 equals 1, but take lambda2 to be minus 1. Then consider also W1 equals W2 equals W. Then we can see that this request can be translated in W minus W must belong to capital W. However, W minus W is the null vector. So we are intrinsically demanding that the null vector belongs to W. It turns out that this expression here, which appears in the theorem, has a huge importance in linear algebra, and for this reason it deserves a special name. The name is provided by this definition, which is the linear combination. Let V be a vector space over the field F, n be a natural number, positive and finite, then any expression of this type here is called a linear combination of the vectors Vj with coefficients lambda j. Notice that when we have n equals 1, it means that we have just one vector. And so, in this case, the only linear combination that we can perform is lambda 1 v1. So remember that in the particular case of just one vector, the only linear combination that we can perform is the multiplication of this vector by a scalar. Using the concept of linear combination, we can restate the previous theorem by saying that W is a vector subspace of V if and only if the generic linear combination of two vectors belonging to W still belongs to W. Thanks to this result and its reformulation in terms of linear combinations, we can discuss some special and important example of vector subspace. Given a vector space V, V itself and the null vector are called the trivial vector subspaces for, I think, self-explanatory reasons. Of course, V is the largest vector subspace of itself because it agrees with itself, and the null vector is the smallest possible vector subspace of any vector space. Instead, a non-trivial example of a vector subspace is provided by the intersection of all the vector subspaces of V. Recall that given any two sets X and Y, their intersection, denoted with this symbol, is given by the set whose elements are those contained in both X and Y. Here you can find an example of intersection, and notice that the intersection is always smaller or at best equal to the smallest subset between X and Y. Thanks to the concept of intersection, we can construct a very interesting example of vector subspace of any vector space V. Consider in fact all the possible vector subspaces of V. Then it turns out that the intersection of all these vector subspaces is a vector subspace of V, and not only that, it is the smallest non-trivial vector subspace of V. You can find the proof of this theorem here. It is not that important to discuss this proof, but I strongly encourage you at least to read it. Now let's pass to the concept of union. One may naturally wonder if the same property, that is, the union of vector subspaces, is still a vector subspace. The answer in general is no. A canonical and very nice geometric example of two vector subspaces of R3 whose union is not a vector subspace of R3 is provided by Wx and Wy. Notice that the vectors belonging to Wx have just the first component, which can be different than 0, and so they are naturally identified with the x-axis. Similarly, the vectors belonging to Wy have just the second component, which can vary, and all the others are fixed to 0, and so this vector space can be identified with the y-axis. As a consequence, their union, as it is written here, can be identified with all the vectors of either the x-axis or the y-axis. Let's now check if W, the union of Wx and Wy, is a vector subspace of R3. We know that when we sum together two vectors of a vector subspace, we remain in the subspace. So, in this case, we consider this vector here, which belongs to Wx, and this vector here, which belongs to Wy, and so they both belong to W. Let's see what happens when we add them together. The sum gives rise to the vector with components 1, 1, 0 that you can see depicted here. We can understand in a very easy geometric way why this vector cannot belong to W. In fact, as you can see, it has a diagonal direction, while the vectors belonging to W have either a horizontal or a vertical direction. So we have found an example of two vectors of W, this one and this one, that sum together generate a vector that doesn't belong to W, this one. And this is enough for us to state that W is not a vector subspace of R3. In linear algebra books, this example is very often chosen to show that the union of two vector subspaces is not in general a vector subspace because it implicitly contains the solution to this problem. In fact, we have just seen that it is the operation of sum which creates obstacles. This suggests to replace the union of vector subspaces with their sum. Consider two vector subspaces U and W of a vector space V, then their sum, as it is written here, is given by all the vectors, which can be written as sum of a vector belonging to U and a vector belonging to W. To have an example, consider again the vector subspaces Wx and Wy that we have just discussed. Then their sum is given by all the vectors W, which can be written as the sum of the generic vector of Wx and the generic vector of Wy, which is the vector with components x, y, 0, with x and y free to vary in R. Notice that with such a definition, the vector given by the sum of 1, 0, 0 and 0, 1, 1, that is the vector 1, 1, 0, belongs to the sum of Wx and Wy, because as you can see, it corresponds to a vector x, y, 0 with x and y equal to 1. This is not a coincidence. In fact, we can prove that not only the sum of two vector subspaces is again a vector subspace, but it is the smallest vector subspace that contains the union of these vector subspaces. As you can see here, I reported the proof of this theorem. This proof is not conceptually difficult, but it's a little bit long. For this reason, we don't have the time to discuss it. However, I strongly encourage you to read it. In the case in which you don't have just two vector subspaces, but a bunch of them, in the literature you can find these notations to indicate their sum. It is important to single out a special type of sum between subspaces. This is called direct sum, and it happens when two vector subspaces intersect just in the null vector. In this case, we write this symbol to denote their direct sum. And more generally, if we have a bunch of vector subspaces that intersect only in the null vector, then we write their direct sum with this symbol here. This theorem shows that having a trivial intersection has an important consequence on the sum. In fact, the theorem states that every vector v belonging to the direct sum of u and w can be uniquely written as the sum of a vector belonging to u and a vector belonging to w. What does it mean uniquely? It means that there are no other vectors other than u and w such that their sum reconstructs the vector v. The proof of this theorem is very easy and very significant. However, before discussing it, I want to show you what happens when we don't have a direct sum of vector subspaces. Consider the three-dimensional real space R3 as our vector space V, and then consider the subspaces U and W defined like this. U is the plane X and Y, and W is the plane Y, Z. Notice that these two vector subspaces, these two planes, share the y-axis, and so their intersection is not reduced to the only null vector, because all the vectors that belong to the y-axis are shared between this and this subspace. Since the intersection of a u and w is not trivial, their sum is not direct, and so we expect that if we take any vector v belonging to R3, for example this one here, then there are multiple choices for the decomposition of this vector as sum of one vector belonging to u and another belonging to w. Let's see that it is indeed the case, because we can take, for example, 2, 1, 0 as a vector belonging to u and 0, 2, minus 1 as a vector belonging to w in order to reconstruct v with the sum. But we can also take 2, 4, 0 as a vector of u and 0, minus 1 as a vector of W, and their sum will again reconstruct the vector V. Hence, the decomposition of the vector V as the sum of one vector of U and one vector of W is not unique. Let's now prove the previous theorem. We are supposing that the sum of U and W is direct, and so their intersection is reduced to just the null vector. Let me write it like this. Okay, imagine that we have two expressions for the decomposition of V as sum of a vector belonging to U and a vector belonging to W. Then, since we have V in both expressions, this means that this vector here and this vector here agree. So we have U plus W equals U prime plus W prime. If we pass U prime on the left-hand side and W on the right-hand side, we have that the difference between U and U prime equals the difference between W prime and W. However, remember that U and W are two vector subspaces, and so they are stable with respect to differences of their vectors. Hence, U minus U prime belongs to U, and W prime minus W belongs to W. As a consequence, this vector belongs to U, but it also coincides with this vector which belongs to W, and vice versa, of course. Hence, both these vectors must belong to the intersection between U and W. But we have recalled before that this intersection is reduced to the null vector. And when do we have that two vectors subtracted to each other give rise to the null vector? When they agree. Hence, U is equal to U prime and W is equal to W prime. And so, the decomposition of V as the sum between a vector of U and a vector of W is unique.
It is now time for a well-deserved recap. As I told you, when mathematicians build a structure, they are also interested in analyzing their substructures. Here we are analyzing vector spaces, and their substructures are called vector subspaces. They are interesting and non-trivial objects to analyze and characterize because, as we have seen, a subset of a vector space may not be a vector space itself. The easiest example is given by the vector space itself without the null vector. What remains is not a vector space. Luckily for us, there is a very simple characterization of subsets of vector space which are vector spaces themselves, and so vector subspaces, which is given by the fact that these subsets of vectors must be stable with respect to linear combinations. So, if you have a bunch of vectors, say v1, vn, which belong to the subset W of the vector space V, then this subset is a vector subspace if this linear combination, that is the sum of the vectors Vj multiplied by any scalar lambda j that we want, where j goes from 1 to n, still belongs to W. On vector subspaces, we can perform operations. The first one that we have analyzed is intersection. It turns out that the intersection between two vector subspaces is still a vector subspace. However, the union of two vector subspaces is not in general a vector subspace, and we have seen that we must replace the union with their sum. Given two vector subspaces W1 and W2, their sum is simply defined as the set of vectors that can be written as the sum of a vector belonging to W1 and a vector belonging to W2. Finally, we have seen that if the intersection between W1 and W2 is reduced to the only null vector, then their sum is called direct, and it is indicated with this symbol here. Remember that the special property of the direct sum is the uniqueness of this decomposition.
In this section, we introduce the fundamental concept of span of a subset of a vector space that will remain with us until the end of this course. In order to define this concept, consider a subset S of a vector space V over the field F, which is not a vector subspace of V. Then the span of S is this set here, given by all the possible linear combinations of vectors belonging to S with scalars belonging to the field F. Remember now that the condition that must be satisfied by a subset of a vector space to be a vector subspace is the stability with respect to linear combinations. Here, with the concept of span, we are defining the span of S as the set which contains all the possible linear combinations of vectors in S. And so it is self-evident that the span of S is a vector subspace of V. But not only that, the span of S has a finer property. In fact, the span of S is the smallest vector subspace of V which contains S. The proof is reported here. Unfortunately, we don't have the time to discuss it, but as always, I strongly encourage you to read it. The concept of span allows us to discuss the family of generators of a vector space, which is another concept that will remain with us until the end of this course. Let me introduce the concept of family of generators with this consideration. Given a subset of vectors S of a vector space V, we have seen that the span of S is the smallest vector subspace of V which contains S. Instead, V is of course the largest vector subspace of itself which contains S. We can ask ourselves what happens when the smallest meets the largest. This is exactly the case in which S is said to be a family of generators for V. That is, the subset of vectors S of the vector space V is a family of generators of V if the span of S coincides with V itself. Moreover, we say that V is finitely generated if it admits a family of generators with a finite number of vectors. If we write the definition of span of S explicitly, we see that the family S is a family of generators of V if every vector belonging to the vector space can be written as a linear combination of vectors of S, which means that there must exist a finite number of scalars lambda1, lambda n belonging to the field F, and vectors v1, vn belonging to S, such that V can be reconstructed through this linear combination here.
The concept of span and family of generators will remain with us until the end of this course. For this reason, it's better to underline them with a short video. Let's consider a vector space V over the field F, and let S be a subset of vectors of V which is not a vector subspace. The span of S is by definition the smallest vector subspace of V that contains S. If S is composed by vectors, say v1, vn, then the span of S is given by all the possible linear combinations of these vectors here. And so the generic element of span of S will be the vector written like this. On the other side, it is clear that V is the largest vector subspace of itself which contains S. Hence, it is a very interesting situation in which the smallest meets the largest. That is, what happens when the span of S is equal to V itself. For what we have said before, this is the case when every vector belonging to V can be written as a linear combination of the vectors belonging to S. If this happens, then we say that S is a family of generators for V. And in this case, we have that V can be written as the span of S.
A trivial family of generators always exists. In fact, V itself is a family of generators. However, this is of course the largest possible family of generators that one can imagine. Instead, as we are going to see throughout the course, what is really interesting in linear algebra is to search for the minimal family of generators in such a way that we can avoid considering redundant vectors. Let's now see what happens when we have two family of generators for the same vector space, in this case we take R2, with a different number of vectors. We start with the family S1, which has these two vectors here. Let's perform a linear combination with generic scalars mu1 and mu2 belonging to R of W1 and W2. What we have is this, and the resulting vector is the vector with components mu1 and mu2. If we consider an arbitrary vector v written with components x and y belonging to R2, then in order to see if we can reconstruct v with a linear combination of vectors w1 and w2, we have to identify v with the vector that we have written here. That is, we have to consider this vector equation and we have to solve it. Solving this vector equation is actually a super simple task because we recognize the fact that in order to solve it, we simply have to equate mu1 with x and mu2 with y. So this is the unique solution of this vector equation, and so every vector v written in this abstract form can be represented as a linear combination of these two vectors here, and so S1 is a family of generators for R2. Let's now consider the second family of vectors of R2, given by the three vectors u1, u2, u3. And again, let's consider coefficients lambda j and perform the linear combination that is written here. The vector that we obtain is this one. As you can see, as first component, we have lambda 1 plus 2 lambda 2, and a second component minus lambda 3. We have to impose the vector equation v equals xy equals lambda 1 plus 2 lambda 2 and minus lambda 3, and we have to solve it. This time it is a little bit more complicated because we have to equate x to this first component and y to this second component. What we obtain is this system of linear equations that can be proven to admit not only one solution, but actually an infinite amount of solutions. In chapter 3, we are going to show how to solve in a very efficient way systems of linear equations, and we will understand why there are infinite solutions to some kind of systems of linear equations. However, I want to show you with an explicit example why we can say that this system of linear equations has an infinite amount of solutions. Consider the vector v equals 1 minus 1. This corresponds to the choice x equals 1 and y equals minus 1. The previous system becomes this one, and as you can see, the second equation is solved just by the unique value lambda 3 equals 1. However, regarding the first equation, we see that there is one equation with two variables. The variables are, of course, lambda 1 and lambda 2. This is why we have an infinite amount of solutions for this system. In fact, as I wrote here, you can choose, for example, lambda 1 equals 1, lambda 2 equals 0, and you have a solution to this equation. But you can also choose lambda 1 equals 1/2, lambda 2 equals a quarter. You inject these two values in this equation and you find a solution. These are just two of the infinite amount of solutions that you can consider. Now notice something very interesting. The family S1 has two vectors, and we could reconstruct in a unique way every vector of R2 by performing linear combinations of these vectors. Instead, the family S2 has three vectors, and as we have just seen, there is a redundancy in this family, and the consequence of this redundancy manifests itself through the appearance of multiple choices for the scalars lambda j in the reconstruction of the same vector. If we consider a family with four or more vectors, then we end up having an even larger degree of freedom in the choice of the scalars in order to reconstruct the vectors of R2 with linear combinations. Let's now see what happens if we consider a third family S3 given by just one vector written with components AB. Imagine now that the geometric representation of this vector is this one, and ask yourselves what are the vectors that we can generate through linear combinations of just this vector here. To answer this question, keep in mind that when you have just one vector in a family, the only linear combination that you can perform is to multiply this vector by a scalar. And since we are considering scalars in R, the only thing that we can do using a vector is to shrink it or to dilate it. And so all the vectors that we can reconstruct by this one through linear combination, that is multiplication by a scalar, are those that belong to the direction, to the straight line defined by this vector here. For this reason, it is clear that this family S3 cannot generate the whole R2. In fact, if you want, consider this vector here. Then you can see that this vector doesn't belong to the straight line defined by the original vector, and so we cannot represent it through a linear combination of this vector. Let's now recap the very interesting information that we have gathered by considering three different families of vectors in R2. First of all, a family with just one vector of R2 cannot generate the whole R2. Secondly, a family with two vectors of R2 can generate the whole R2, and if it does, the decomposition of any vector of R2 as a linear combination of the vectors of this family is unique. Thirdly and finally, also a family of three or more vectors of R2 can generate the whole R2, but if it does, the decomposition of any vector of R2 as a linear combination of these three or more vectors is non-unique. The analysis that we have just performed suggests that the minimal number of vectors of a family of generators is related with the uniqueness of the decomposition of a vector as a linear combination of these generators. We are going to see in the next section that this intuition is actually correct. Before passing to the next section, I want to underline that we have seen before that vector equations can be rewritten as systems of linear equations, and this confirms what I told you in section 1.1. That is, the theory of vector spaces is intimately related with linear equations, and so, to be able to solve them, we need the scalars appearing in these equations to be contained in a field. What I said before regarding the concepts of span and family of generators is also valid for the concepts of linear dependence and independence of vectors. That is, all these are foundational concepts in linear algebra and they will remain with us until the end of this course. As always, I prefer to introduce these concepts using the geometric intuition offered by geometric vectors in the real plane R2, and then I will show you how we can turn this intuition into an abstract property that can be defined for every abstract vector of a vector space. The geometric property that we need as a motivation is the so-called collinearity. Given two vectors v and w, we say that they are collinear if they lie on the same straight line, that is, if they have the same direction. Here and here you can see two examples of two vectors which are collinear, and in this case they have also the same orientation. In this case they have opposite orientation. What's important about collinearity is that when two vectors have the same direction, then we can write each of them as the other times a non-null scaling factor given by a scalar, which is positive when the vectors have the same orientation, as in this case, and negative in the other case. To fix the ideas, let's consider W as lambda times V, where lambda is a non-null scalar. Then we can rewrite this equation as W minus lambda V equals the null vector. Notice that on the left-hand side of this equation, we have a linear combination of vectors W and V. In front of W we have 1, in front of V we have minus lambda, and we sum 1 times W plus minus lambda times V, and this is a linear combination. On the right-hand side, we have the null vector. This means that when two vectors are collinear, we can decompose the null vector as a linear combination of these two vectors with non-null coefficients. Let's see if we can do that with non-collinear vectors v and w. So we are supposing now that v and w don't lie on the same straight line, they don't have the same direction, and we are trying to see if we can write a linear combination with non-null scalars lambda and mu, such that we can reconstruct the null vector with this linear combination. As you can see here, this is equivalent to say that mu times w is equal to minus lambda times v. Then, since both mu and lambda are different than 0, we can divide both sides by both of them. We choose to divide both sides by mu, for example, and we remain with w equals minus lambda divided by mu times v. But this coefficient here is a non-null scalar, and we are saying that w is a multiple of v times this scalar here, and so v and w are collinear. This is, of course, a contradiction with respect to the hypothesis of non-collinearity, and so the fact that we can write a linear combination of two non-collinear vectors and we get the null vector by using non-null coefficients in the linear combination is just not possible. The consequence is that if we want to perform a linear combination of two non-collinear vectors and obtaining the null vector, then we have to impose that the scalars appearing in the linear combination are both null. As always, when we use a geometric argument to have an intuition, we pass from dimension 2 to dimension 3. In this case, if we repeat the same reasoning, we discover that the linear combination of three non-null vectors u, v, and w belonging to R3 can give rise to the null vector of R3 with non-null coefficients if and only if the three vectors belong to the same plane. This means that there exist two scalars lambda and mu such that w is equal to lambda times u plus mu times v. In this case, we say that the vectors are coplanars. If the three vectors are not coplanars, then the only way to obtain the null vector with a linear combination of them is to use all zero coefficients. R2 and R3 offered us a very nice geometric intuition thanks to the concepts of collinearity and coplanarity. However, if we consider an abstract vector space, these concepts are lost. Luckily for us, the algebraic property related to the nullification of a linear combination remains completely intact, because this concept can be stated for every vector space and not only for R2 and R3. As you see, the pattern is always the same. First, we have a nice geometric intuition in R2 and R3, and then we translate this intuition into an algebraic property that we can use and extend to all kinds of vector spaces. The algebraic property that we have highlighted before distinguishes between linearly dependent and independent vectors, as we are going to formalize in this definition here. Let's consider any vector space V over the field F and a family S of vectors in V. Then these vectors here appearing in the family are said to be linearly independent if we can obtain the null vector of V by a linear combination of these vectors if and only if all these scalars are zero. Otherwise, if at least, pay attention, at least one of these coefficients, lambda j, is non-zero, then the vectors v1, vn are said to be linearly dependent. In linear algebra, we also say that a family of linear independent vectors is a free family. As you can imagine, with the word free, mathematicians underline that linearly independent vectors are free from linear links between them. There are some special cases that it is better to underline immediately. Let's start with the first one, given by a family of vectors composed just by one vector. If we have just one vector, then the only linear combination that we can perform is to multiply this vector by a scalar lambda, and saying that lambda times v equals the null vector is solved if and only if lambda equals 0, means that v is not the null vector. So a one vector family is free if and only if the vector that composes this family is not the null vector. The second special case to highlight is when the null vector belongs to a family of vectors. In this case, the family can never be free. In fact, if we multiply the null vector by any scalar, we get back the null vector itself. I urge you to verify what I just said by considering the special case of a family with just two vectors, the null vector and another non-zero vector. Try to do it. This is actually a very nice small exercise from which you can learn a lot about linear dependence and independence. The following theorem contains a very nice characterization of linearly dependent vectors. It says that a set of vectors v1, vn of any vector space V is linearly dependent if and only if there is at least one vector that can be written as a linear combination of the others. Here you can see the proof is not difficult at all. As always, I urge you to read it. However, as you can see, is a little bit long, and so we skip it and we go to the next theorem. The theorem says that if we have a bunch of linearly independent vectors of a vector space V over the field F, then if a vector V belonging to this vector space can be written as a linear combination of these vectors, that is, if there are scalars lambda 1, lambda n belonging to F such that V can be written like this, then these scalars are uniquely determined. There are no other scalars than this one here, such that V can be written as a linear combination of these vectors here. Suppose that the vector V can be written in two ways as linear combination of V1, Vn. The first is with coefficients lambda 1, lambda n, and the second is with coefficients mu1, mu_n. The vector V appearing in the linear combinations is exactly the same, and so we can write the equality between them. This is exactly what I wrote here, and this in turn is equivalent to write this. That is, using the compact notation, we have the sum for j that goes from 1 to n of lambda j minus mu j times vj equals the null vector. However, we are under the hypothesis that the vectors v1, vn are linearly independent, and here we are writing a linear combination of them, obtaining the null vector. This is possible if and only if all these scalars are 0, but these scalars are 0 if and only if these coefficients are all equal. So this linear combination here and this linear combination here are exactly the same.
Since the beginning of this course, we have seen that we can generalize intuitive geometric concepts using linear algebra. Thus, we may wonder if we can generalize the concepts of collinearity in 2 dimensions and coplanarity in 3 dimensions. Two vectors in the plane are collinear if they have the same direction, and so if they lie on the same straight line, for example, these two here. Instead, in the 3-dimensional space, two vectors are coplanar if they belong to the same plane, for example, these two vectors here that belong to the plane pi. We have seen that the concept of linear dependence allows us to generalize these two intuitive concepts to more than 3 dimensions. A bunch of vectors v1, vn is said to be linearly dependent if they can generate the null vector with a linear combination that has at least one of the scalars that is non-zero. If this cannot happen, that is, this equation implies that all the coefficients lambda j are 0, then we say that the vectors v1, vn are linearly independent. So, in particular, linearly independent vectors in 2 dimensions are vectors that don't belong on the same straight line, for example, this one here. Instead, in 3 dimensions, linearly independent vectors are those that don't lie on the same plane, for example, this one here. The most important property of linearly independent vectors is related with the possibility of developing a vectors as a linear combination of them. If this is the case, then the scalars appearing in the linear combination are uniquely determined. Even if this property doesn't resonate with you in this moment, keep it in mind because it is essential for what comes next.
In the previous two sections, we discussed what it means for a family of vectors to generate a vector space and to be linearly independent. Building on this foundation, we can now introduce the most crucial concept related to vector spaces, the basis. Consider a family of vectors denoted with S, composed by the vectors v1, vn belonging to the vector space V over the field F. Then S can be a family of generators of V, but it can also be a free family, that is, all the vectors v1, vn are linearly independent. Of course, it is not forbidden by the law for S to have both features at the same time. Let's see what happens in this case. For F to be a family of generators of V, it means that every vector belonging to V can be written as a linear combination of the vectors v1, vn. But if the vectors v1, vn are linearly independent, then this linear combination is uniquely determined. To resume, if S is a free family of generators, then every vector belonging to the vector space V can be uniquely written as this linear combination here. That is, the scalars lambda 1, lambda n are uniquely associated to the vector v once the family S is specified. In the following examples, we're going to see that also the order of the vectors in S is important. For this reason, in the following definition of basis, we explicitly consider also the request of ordering. Now, the formal definition of basis of a vector space is the following. A basis of a vector space V is an ordered family of vectors indicated with B, which has the property of being free and to generate V. Notice that in the mathematical literature, the curly brackets, like these ones here, denote a non-ordered set, while the parentheses, like these ones, denote an ordered set. Hence, from now on, we will use this notation to indicate an ordered set of vectors that correspond to a basis. As we have just said, every vector of V has its own personal linear combination with respect to the basis vectors. So we must expect for two different vectors V and W a different set of scalars lambda 1, lambda n, and mu1 and mu_n that appear in the corresponding linear combinations. In linear algebra, these scalars have a precise name and they are called the components of the vector v with respect to the basis b. Let's immediately give an example of a basis of a vector space. For the vector space, consider the nth Cartesian power of the field f, which as always we take to be either R or C, then the so-called canonical basis of Fn is given by the ordered set of these vectors here. As you can see, the coordinates of the jth vector of the canonical basis are all 0 except for the one at the position j, whose value is precisely 1. So E1 has 1 in the first position and 0 otherwise. E2 has 1 in the second position and 0 otherwise. And En has 0 everywhere except for 1 in the nth position.